In this lecture, we are going to look into the definition of a category and some of its examples. So, without any further ado, we just start off with the definition. Observe that the definition of the category will be given completely in terms of sets. So a category A is where A0 is a set called the set of objects of A. We have A1. Let me put this a little bit. We have A1 as another set called the set of morphisms of A. There are three functions are functions with del 0f being the domain object of f and del 1f is the codomain object of f, and we put a symbolism here and we would write or to denote f is a morphism with the domain object being A, codomain object with B, while hom AB would be the set of all morphisms such that okay. All right. we would have a special function also, is a function which we shall write like this. This is the identity morphism. For for the object this, and given just this data, we can create this set which is the set of all composable pairs no, why am I doing it? There is also a reason why am I doing it. Is a set of all is a set of all composable pairs of composable pairs of A and M is a function with the moment I have this set with the functions defined by and M is a function called the composition with the composite of observe, actually in this picture the ones this A2 is actually given. The moment we have others, A2 is given, And so also are these two maps. The moment I define A2, I actually have defined these two maps also. Okay? And the defining condition of A2 is actually given by the equation, by two equations, partial 0 P0 is equal to partial 1 P1. That's exactly the defining condition of A2. Now, these are subject to the following conditions. So, what is it? The first one is saying partial 0E is the identity on this. So if you compose this, so that means I am saying that the domain object, that means I am saying that the domain object of the identity arrow is A, and so is the codomain object. Okay? So both are A. And then I want to say so, in other words, if I take a composable pair, so this is the composite. I want to say that the domain of the composite is the domain of del 0 P1. Because over here GF, yes, the domain of the composite, which is A, is the domain of the second component of the composable pair. The codomain is the codomain of the first. Yeah, so that's what I want to say. Yes, and then if then I want to say F compose the identity. So that's why it's actually the identity. So this is kind of saying that the identity morphisms are really the identities with respect to the composition. And finally, if A okay. Observe, one thing is clear, that if so let me put that as a remark, as a separate remark. HGF and HG belonging to A2 implies okay. So this is the observation. So that actually validates this last equation. So this one is often said to be the associativity of the composition, and this is about the identities. So this is exactly a category. So whenever we are going to specify a category, we will actually have to specify these two sets, these 4 functions, and check these 4 equations. Many a time just drawing pictures will be sufficient, and we will now look into some examples. So we have seen now this definition of this category. We'll now look into several examples. Obviously, first comes the motivating examples. So we had in our mind the category of sets, for instance. In this case, set 0 is just the set of all sets. Set 1 is the set of all functions. And partial 0, partial 1, the usual domain, codomain of functions, and E and M, the usual identity function and usual composition. Okay. So that gives us the category set. As a similar one, we have the category of groups, where group 0 is the set of all groups, group 1 is the set of all group homomorphisms, and the rest are usual. Similarly, we have the category of topological spaces, the category of rings, and the category. So these are two different. This is the category. This is the category of rings with identity and homomorphisms preserving the identity. While this is the category of rings which may not have an identity and ring homomorphisms. So for instance, the ring of even integers is an object in Rng, but not an object of Ring, because even integers doesn't have an unit. Okay. Also, the morphisms are different in the sense, if we take integers, from integers to integers, the morphisms in Rng and the morphisms in Ring are different. Okay, so let's keep this as an exercise. Show that the morphisms in ring and ring are different. Okay. All right. I shall be leaving many such exercises which will be the basis of the assignments that follow this video lecture. Okay. So we have the category of, coming back, rings with identity or rings without identity. In general, therefore, any kinds of sets with some structure and structure preserving maps. All of these are examples of a category. So now for some other examples. Firstly, let X be a set. And I am trying to give you so as the set of objects, I take the set itself. as a set of morphisms, I also take the set itself. And my partial 0 is the identity map. Partial 1 is the identity map, and so also is the E. Okay. Now, let us try and see what am I trying to do. Obviously, if I take this, so I have partial 0, partial 1 and E all as my identity of X. So the first equation is satisfied automatically. There is nothing to look for it. So then suppose if I take an xy from X, what is hom xy? So these are morphisms. So z from this x again, such that partial 0 z is x and partial 1 z is y. So it means it is z such that x is equal to z is equal to y. So in other words, it turns out that hom of xy is the singleton x if x is equal to y, and is the empty set if x is not equal to y. So the picture seems to look like this. So if this were the set X, and if I took an object, an element over here, well, these are the objects. There is only one morphism, and remember, when x is equal to y, this single x is actually my E of x. Okay, so there is only one morphism here, and that's the picture, nothing connecting them. Okay, so therefore what will be, let's see, if this is the picture, so what will be my composable morphisms? So this will be x pairs from x cross x such that partial 0 x is equal to partial 1 of y, so which is the same thing as, so this means x is equal to y, so is that partial 0 x is my x, this is equal to y, so this means it is this subset. And this is obviously in bijective correspondence with the set X itself. So I take the composable morphisms also to be X. P0 is also then the identity. So this is also equal to P0, P1, and my M. Okay, so of this one should be, as I said, it is already given, so just in line with my diagram. So I 1 2 3 4 5 6, so that's the category. Okay, so what is the picture? The picture is, the moment I take a set X, I can make its elements, I can make this, consider the set X as a category whose objects are the elements and morphisms are nothing else but the identity maps. Okay. So this gives rise to something called a discrete category. A category A is said to be discrete if and only if for any two objects HOM AB is non-empty if and only if A is equal to B and HOM AA is nothing else but the identity. Alright? So it turns out that every discrete category, every set gives rise to a discrete category, and the set of its objects of that is nothing else but that set. Therefore, if I start off with a discrete category, this tells me its picture is exactly like this. So, I show that the discrete category are precisely given by sets. So in what do I mean by this? I'll make this this is a very, very loose statement. What I mean by this statement, what will you have to show, is given a set, as I have shown, I can produce a discrete category. Conversely, given a discrete category, I can produce a set whose discrete category as produced in this construction is nothing else but the given discrete category. Okay, so you go and come back as if. Let's see another example. So this was in which, in some sense, the morphisms were trivial. Now let's make the objects said to be trivial. So let X be a set again. And we now take the set of objects to be singleton. It has only one object. And I take my set of morphisms to be that set X. Now from any set X to the singleton, that obviously exists one and only one map. So the map partial 0, the domain and the codomain are exactly same. So and I have this map. I say E star is, say, let me put some, let me say, let it put it to be, say, U. It's an element. Okay. Now, obviously, obviously partial 0 E is equal to partial 1. There is no question about it. Now, so what's the picture like? The picture seems to be suggesting is I have this single object and the morphisms are something like this. And there is a very, very special morphism, as I said, this U. So therefore, for x and y in X, so what is the composable pairs? Therefore, the set of all, every pair is composable, and the projections are the usual product projections, and there exists a M. So therefore, M is a binary operation. Is a binary operation. On X. Further, U is the identity. That means X, U is equal to X implies U is the identity. And the associativity then says the binary operation is associative. So it's an associative binary operation with an identity, and hence X is a monoid. Okay? Hence X is a monoid. So if conversely, suppose I have a one object category, then the picture is exactly like this. So one object category makes X a monoid, that's it. And so conversely, if I have a monoid, I can make it into a one object category as described. So that's also the third exercise. So we have now seen two extreme cases when the set of morphisms can be made very trivial, and that's the discrete case, and when the set of objects can be made very trivial, the singleton case, and hence we have monoids. We go back again to another flavor of of the set of morphisms made trivial. So this time we say that A is a category such that for AB in objects, the Hom set of AB is at most a singleton. That means either it is empty or there is at most one morphism. So it's exactly singleton when it's not empty, otherwise it's empty. So in this case, let us define if then obviously this, because the identity is already there in Hom AA, and that is exactly the Hom AA. And if A is less than or equal to B and B is less than or equal to C, this implies Hom AB is non-empty and Hom BC is non-empty. So that means, and it is exactly singleton, so there exists a morphism, a unique morphism here and a unique morphism here. So under composition there will exist a morphism. So this says Hom AC is non-empty and hence okay. So is a pre-order on this. Conversely, if X is a pre-order, X be a set with a pre-order, then I take the set of objects to be X. The morphisms is precisely the set of the relation, the subset of X cross X. Then I want to define my partial 0 and partial 1. So partial 0 is the smallest. So partial 0 of xy is the smaller of x and y. The same as saying x is less than or equal to y, and partial 1 of xy is the larger. Okay, and what is my E? So E of x is obviously xx, which is in this. Okay. So now let us look into Hom of, so I take an xy in x. What is Hom? So this is exactly uv in this such that the partial 0 of uv is x and partial 1 of uv is y. So this means uv in x cross x, firstly u is less than or equal to v, partial 0 of uv is u and v is y. So this is exactly nothing else but the pair xy. So in other words, therefore, hom of xy, so I can write it here, this will be this. Well, this is true if x is less than or equal to y, and if we had taken a pair xy for which, so again, what is the picture? The picture is we have a pre-ordered set. If we have this y is larger, so as if we are drawing the hash diagram of the pre-order. So that's the unique morphism. Okay. So what is my composable pairs? Say C. So it's, by my definition, from such that partial 0 of PQ is partial 1 of U. So this means this is PQ UV in, so this is this. Let me simplify this statement. This is nothing else. PQ is in relation, so P is less than or equal to Q, so partial 0 is P and this is equal to V. So which means this set is in bijective correspondence with P, Q, U, such that P is less than or equal to Q, and P is less than or equal to Q and U is less than or equal to P. Okay. So we can actually write this in another way. U, P, Q such that, okay, so C is this, so let me call this set to be C. Alright, so I take C to be here, and then what would be my P0? Remember, it takes the first, so it takes over here the next two coordinates, the second and the third, P1 is from, this will therefore take UV, so UP actually, the first two coordinates. So that's my P0 and P1. And what about my M? So M is the transitivity. So M is taking UPQ to UQ. Okay. And then the rest of the axioms are satisfied. So this is verification. Therefore, that is my next exercise is exercise 4. Verify that the preordered sets precisely determine the categories in which the Hom sets are at most singletons. And compare with discrete categories. Okay, so that's the situation about trivial set of morphisms being trivial. As a special case, so we have the category 1, it is a category with one object and plus one morphism. The category 2, which is just this. The category 3, which is this. And obviously you have this. Okay. The category 4, so we'll stop now drawing the composites. So all possible composites are there. So all possible chains. So in particular, the chain with n elements provide the category n. Okay, and so on. And then obviously we can obviously have the category which has no objects. So the empty set. Produces in the category 0. So it has no objects and no morphisms. Alright? Okay. Let's have another example. This should be example 6. So this time my set of objects is the natural numbers. And what are my morphisms? Well, the morphisms are the set of all matrices. Okay? So, objects are natural numbers. Morphisms are set of all matrices. So of order m cross n for with real entries. So let me write this in this way: all matrices. Set of all matrices, m cross n order matrices with real entries. Okay. Now what is this partial zero? So if A be an n cross n matrix, then I will say that partial zero of A is n and partial 1 of A is n. So that means an m from the number of columns to the number of rows. Okay, matrices. And what is my E? E is the identity matrix of order n. And E of n is In, the identity matrix of order. Okay, so what's my composition? So what are the composable pairs? Well, so what is this? What is C? So C is a set of composable pairs what is it? It is those matrices, okay, pairs of matrices such that the number of columns of A is equal to the number of rows of B. Okay, so it's something like this. So the number of columns of A, the number, so something, the number of columns of A is equal to the number of n cross B, yes, rows of. Okay, and then what's the composition? So M, the composition. So this is an M cross N, this is an M cross P. So it's an M cross, yeah? So it's the matrix multiplication. So M is just the matrix multiplication. Okay? So given this, this is actually, one can, obviously this composition is associative, it's the INs are the identities. So this gives us another category. And in fact, this category is precisely the category of interest in the finite dimensional vector spaces. This is the category of interest in the theory of finite dimensional vector spaces. Okay. All right. Before we give some other examples, we would need another notion, that is the notion of a functor. Recall, whenever we have had a structure, there was a structure preserving map. Category itself comes with a structure. And what is it? The structure is, well, there are objects, there are morphisms, there is a codomain, domain of a morphism, there is the identity object, and there is the composition. So a functor we'll even write like this: from a category A to B is, remember, A is actually given by this 6 tuple, and B is given by a similar 6 tuple, and what I am saying, a functor f is a pair of functions is where f0 f1 are functions such that, firstly it takes objects. To objects, morphisms are mapped to morphisms, but I must have the domain and codomain of a morphism to be. So that means if then f1 of f should be from f0 of a to f0 of b. So what am I saying? So that means I am actually, with respect to this diagram, I am saying f0 partial 0 is partial 0 f1 and f0 partial 1 is partial 1 f1. That means the top square and the bottom squares commute. Secondly, for any a object, the identity morphism on A must be the identity morphism on F not A. So which is, I am saying that is F, that is, I am saying EF1 is equal to EF0 is F1E. Okay. So in other words, this part of the diagram reasonably commutes. The top squares commute, the bottom squares commute, and the middle squares also commute. Okay. And finally, there is another structure which is the composition. If in A, then F1, this is F1G composed F1F. Okay. There's something to be checked whether F1G, but the first condition immediately says that if GF is composable, then F1G and F1F are composable. Okay. So just as a remark, under A, GF is in A2 implies F1G and F1F is in B2. So that there is this function okay. There is this function, and hence C says something. So you automatically have this function, and then C says that with this function the left square commutes. So that means MF2 is F1. Okay, so it's a functor is a pair of functions. F0 is often said to be the object part of F, and F1 is said to be the morphism part of F. Okay. Now, henceforth, we will just drop the subscripts, for it's an abuse of symbol. F0 and F1 replaced by F. So what does it say? It takes objects to objects, morphisms to morphisms, such that if so A becomes F if then f of F is from f of A to f of B, where here I mean obviously the object part of F coming into the picture, here the morphism part of F coming. So this is actually F1, this is actually F0. F of 1A is 1 of FA, and C becomes if then okay, so in this simpler language. So this is a function, this is a functor. Okay, let's now look into some more examples of categories and functors themselves. Well, carrying on, I think it should be. So then let's have example 7. For functors, for instance, if you take the category of groups to the category of sets, if the underlying set functor, so which takes for a group X is the underlying set of X, and for a morphism, for a group homomorphism, U of F is the underlying function of the group homomorphism. F. This is an underlying set, or we often say we forget the group structure and hence we give it the name the forgetful functor. Similar forgetful functors from abelian group to sets, from topological spaces to sets, from rings to sets, from rings to sets. But there is also a forgetful functor where we forget the commutativity and we can come to groups itself. Okay. Also, this is the inclusion. It's just okay, and we can come to. We can forget the multiplication to come to the abelian group of. We can also come. We can forget the addition and come to the commutative monoid. Okay, or let's do it here. We can forget this is the category of monoids. Okay, we forget the addition and come to the category of monoids. So there are several forgetful functors. Sometimes even we will see later on that sometimes we can have a nice functor from group. We can add structure. So given a group, we might abelianize it. Okay. So there can be some. Okay. Let's have another kind of example. Suppose A and B are categories. Then we obtain another category whose objects are, what is this category? Its objects are this, its morphisms are precisely this. So this is the codomain part, the domain part, and the identity. The composable pairs are exactly this, and this is M cross M. So in short, what are the objects? The objects are pairs of objects, A coming from A, B coming from B. And what are the morphisms? They are again pairs of morphisms. A to C in A to C F, A to C in A, G, B to D in B. And composition is just by component wise. And the identity of AB is identity of A and identity of, that's the meaning of this. Okay, so that's the category. We can check. But what is more interesting is that from this category there are two nice functors. Well, what does P0 do? So AB is taken to the first component, okay, and what does P1 do? It obviously takes to the second component. Okay, so that's the picture. But it is not only this too. Suppose you have another arbitrary category X, and you have the category, and you have two functors. So you are given the functors f0 and f1. There is the unique functor and what does it do? There is a unique functor which makes this diagram to commute. And it does the most obvious thing. Okay? It does the most obvious thing. So, there exists a unique functor such that f0 is p0f and f1 is p1. Aha! I didn't define the composition of functors. So, but then it is quite natural. So it's quite natural. So I leave it as an exercise. Define composition of functors so few more things. It's left as an exercise. Define composition of functors. Define identity functor. Show that composition of functors is associative. And the identity functors are identities with respect to the composition of functors. Right? So that's an exercise. You define them, and then can you see a category here? That's my is a probing question. Okay. All right. Now let's have another example, and that is say of the category of arrows. So let A be a category. And I'm just saying And what is this? Objects are morphisms. Okay. Now what is a morphism over here? So I have a picture like this, and I want a morphism here. So it is just a pair of morphisms where U and V are also from A1 and GU is VF. This diagram. Obviously by pasting, so if you compose, so what would be the composite? So you'd have another such thing, and then you compose this left hand side, the vertical ones, and the right hand side, so that gives it. And that composition has to be associative and the identities. So I leave it again as an exercise. Specify the sixth tuple. Okay. All right. And then finally, let's have another category. Suppose we have a picture. So we have something like this. We just give some such picture like this, but we specify nothing about the identities or whatever. Can I make this, can I extend this into a category? Well, yes. If I have to extend this into a category, then I must insert some more morphisms. This morphism has to be inserted. So I insert this. Now there will be a morphism from B to B, because you go from B to A and come back. So there is AB. Similarly, there shall be a BA. Now, you have a loop over here. So, you come from A to B and then follow it by this loop. So, you should have ABA. Okay. Similarly, you come from B to A and then follow it by this loop. So, it should be BAB. Okay, and so on. Again, there is this loop. Furthermore, BAB. So, AB, you go AB and then ABA. So, otherwise, so there shall be many such compositions. Okay, over here. And then I have to introduce the identities. let me keep them at the same level. So these are the new introductions that I have made. And let me use the same color, so without producing any further confusion. So then if I started off with this piece of a diagram, we can extend this now to a category. We can extend this to a category, which we say P. Obviously, this diagram, the most natural thing to think of, if we have such diagrams, we can think of morphisms between such diagrams, which preserves the vertices, preserves the arrows, in the sense that the domain and the codomain. So, a morphism of oriented graphs, in a sense. Okay. So, this oriented graph A is actually, in some sense, inserted. As this is a graph homomorphism, so it is inserted inside this category. Every category is an oriented graph in particular. But there is something nice. Furthermore, if I have any other category and a way to oriented graph homomorphism from the oriented graph A to that oriented graph of X, then I am saying that there will exist a unique functor if I might call this as I, such that f star I is f star composed I. A similar composition of such things can be defined and so on. So there will exist a unique functor. And what would be this? Say, let me try and give an example. Obviously, if this has to be a functor, then this must go to this. Okay? So f star of A, B, C must be F. Okay? And then what should be f star of A should be f of A. But what should be f star of BA? Say BAB. Well, if it has to be a functor, then it should be FB, FA, FB. And that is well defined because these are morphisms in X which can be composed. So that actually gives an idea of how you define this functor f star. So I leave this as a probing exercise. Can you make this example clearer? With that, I'll stop.